Femtosecond hard X-ray pulses are an important tool for unraveling structure changes of condensed matter on atomic length and time scales. A novel laser-driven X-ray source provides femtosecond copper K-alpha pulses at a 1 kHz repetition rate with an unprecedented flux of some 10 to the power of 12 X-ray photons per second. Elementary processes in physics, chemistry, and biology are connected with changes of the atomic or molecular structure on a femtosecond time scale. 1 femtosecond, fs, equals 10 to the power of -15 seconds. Ultrafast X-ray methods hold strong potential for following structure changes in space and time and generate movies of the motions of electrons, atoms and molecules. This perspective has resulted in a strong demand for femtosecond hard X-ray pulses to be applied in X-ray scattering and spectroscopy. There are two main approaches to generate ultrashort hard X-ray pulses. The first are sources based on large-scale electron accelerators and undulators in which femtosecond electron bunches radiate bright X-ray pulses. The second are small-frame laboratory sources driven by intense femtosecond optical lasers. Here, electron acceleration occurs in the strong electric field of an optical pulse, and X-ray pulses are generated by collisional interaction of such electrons with atoms of a metal target, similar to a conventional X-ray tube. Researchers at the Max Born Institute, MBI, in Berlin have now accomplished a breakthrough in tabletop generation of femtosecond X-ray pulses by demonstrating a stable pulse train at kilohertz repetition rate with a total flux of some 10 to the power of 12 X-ray photons per second. As they report in Optics Letters, the combination of a novel optical driver providing femtosecond mid-infrared pulses around a 5 micrometers, 5,000 nanometers, wavelength with a metallic tape target in a transmission geometry allows for generating hard X-ray pulses at a wavelength of 0.154 nanometers with very high efficiency. The optical driver is based on optical parametric chirped pulse amplification, OPCPA, and provides 80 fs pulses at a central wavelength of 5 micrometers with an energy of 3 millijoules and a repetition rate of 1 kHz. To generate X-ray pulses, the mid-infrared pulses are tightly focused onto a thin copper target. In an optical cycle of the optical field, electrons are extracted from the copper tape, accelerated in vacuum and steered back to the target. Electrons with a kinetic energy of up to 100 keV re-enter the target and generate bright copper K-alpha pulses at a wavelength of 0.154 nanometers, accompanied by spectrally broad bremsstrahlung. The longer optical cycle of the mid-infrared pulses compared to pulses at shorter optical wavelengths results in longer acceleration times of the electrons, higher kinetic energies, and eventually higher efficiency in X-ray generation. The new table-top X-ray source reaches an average number of K-alpha photons up to 1.5 x 10 to the power of 9 photons per pulse in the full solid angle, or 1.5 x 10 to the power of 12 photons per second. This photon flux is 30 times higher than from commonly used table-top X-ray sources driven by sapphire lasers at the central wavelength of 0.8 micrometers. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.